Welcome to The Explainer. Today, we're going on a journey from waste to wealth, looking at exactly how wastewater plants are transforming into actual resource factories. You know, every single time you wash your hands, run a load of laundry, or flush the toilet, you're tapping into this massive, completely hidden infrastructure network. And for decades, we've really just viewed this as waste management, right? It's just this necessary, highly expensive burden to keep our cities clean and our rivers from getting polluted. But today, we're going to dive into the absolutely incredible technological shift happening right under our feet. We're finally moving away from just throwing things away. Instead, modern engineering is literally turning so-called wastewater into a total goldmine of clean energy, vital agricultural nutrients, and crystal clear reclaimed water. Okay, before we get into the how, let's just talk about this massive number. Traditional wastewater treatment plants consume between 1 and 3% of our total global energy output. Actually, pause and think about that for a second. That is roughly equivalent to the entire energy consumption of a major industrialized nation, just to treat our dirty water. On a global scale, it's absolutely astronomical. We're talking 20 to 45 kilowatt hours per person connected to the grid. In a lot of municipalities, your local water utility is literally the single largest consumer of electricity in the whole city. It is a massive financial and environmental drain. But to understand why these plants are such crazy energy hogs, and more importantly, how we're finally fixing it, we need to look at how they actually work. So here is our roadmap for today's explainer. First, the linear water problem. Second, step 1, preliminary and primary. Third, the aerobic energy hog. Fourth, anaerobic digestion generating power. And finally, number 5, the ultimate resource factory. All right, part 1, the linear water problem. Historically, we've relied on this really flawed straight-line model. Take, make, use, and discharge. We extract fresh water from rivers or groundwater, we treat it to make it safe to drink, we use it in our homes and factories, and then we just dump it right back into the environment. Sometimes it's treated well, sometimes not. But by only using that water molecule once, we're not just stressing out our natural water supplies, we are completely missing out on harvesting the incredible resources locked inside that discharged water. It's a huge missed opportunity. Moving right along to part 2, step 1, preliminary and primary treatment. So when raw sewage first hits a facility, it's basically just physics at work. The preliminary phase is all about physical screening. We're just filtering out the big macroscopic stuff. Twigs, plastics, rags, you name it. And this is absolutely crucial just to protect the delicate pumps further down the line. Once the big stuff is gone, we move to primary treatment, which is mostly just sedimentation. The water sits in these massive clarifier tanks, and we literally just let gravity do its thing. The heavy stuff settles to the bottom as sludge, the lighter stuff floats to the top to be skimmed off. It works great for solid particles, but the water still has super high levels of dissolved organic matter that gravity just can't touch. Which brings us to part 3, the aerobic energy hog. Now, to get rid of all that dissolved organic matter I just mentioned, traditional plants use aerobic digestion. This relies on what's called activated sludge. Basically, we use a very hungry workforce of aerobic microorganisms to just eat the biodegradable waste. But because they're aerobic, they need oxygen to survive. So the plant has to artificially supply it by continuously pumping massive amounts of air into the bottom of these deep tanks, bubbling it all the way up. It's this incredibly aggressive, non-stop mechanical process. And here is the kicker. This single oxygen-hungry step uses more than half of the entire facility's energy. Remember that 1 to 3% of global energy stat? Yeah. The vast majority of that is quite literally just powering giant, expensive bubble machines to aerate dirty water. Plus, this whole aerobic process creates tons of excess biological sludge because those little microbes keep multiplying, which means we have to spend even more energy and money to dehydrate and dispose of them. It definitely cleans the water, sure, but from an efficiency standpoint, it's a tremendous bottleneck. But what if we just turned off the oxygen? Let's dive into part 4, anaerobic digestion and generating power. When you starve the process of air, you get a completely different reality, anaerobic digestion. This uses a totally different set of microorganisms that actually thrive without oxygen. A great example of this is the UASB reactor. That's an upflow anaerobic sludge blanket. The raw sewage flows upward through a suspended layer of biological sludge. Because we aren't pumping in oxygen, the energy demand just completely plummets. But here's the real magic. As these anaerobic microbes eat the pollutants, they don't just multiply and create a bunch of excess sludge. Instead, they convert that organic matter directly into highly valuable biogas.
We're talking mostly methane and carbon dioxide. That gas bubbles up, gets captured at the top, and boom, we can use it as a direct energy source to generate heat and electricity for the plant itself.
Putting these two methods side by side, the paradigm shift is just undeniable. We go from this energy-draining aerobic process that constantly needs air and makes a ton of waste sludge to an anaerobic process that needs zero oxygen, makes very little sludge, and literally generates its own power. It's kind of like having a tiny army of alchemists turning the very pollutants that cost us a fortune to remove into alternative energy. And when you combine this with advanced filtration, like an ANMBR system, we can capture all this energy while putting out perfectly clean, reusable water. All right, final section, part 5, the ultimate resource factory. So, instead of just dumping water back into a river, modern circular facilities are extracting 3 distinct, super valuable resources. First up, clean water. By using advanced ultrafiltration membranes, we reclaim water to such a high standard that it's perfect for agricultural irrigation or industrial cooling, which saves our precious, fresh surface water. Second, energy. Like we just talked about, capturing that methane biogas lets these facilities generate their own electricity, pushing them toward becoming zero carbon or even energy positive. And third, materials. Wastewater is absolutely packed with nutrients like nitrogen and phosphorus. If you dump those in a river, you get toxic algae blooms, but if we extract them using precipitation technologies, they become incredibly valuable, highly sustainable fertilizers for our farms, replacing the need for carbon-heavy mining.
Which leaves us with this fascinating final thought. The technology to do all of this, to completely close the loop, already exists today. We can capture the energy, we can harvest the nutrients, and we can reuse the water. The only hurdle now is scaling these innovations and ditching that outdated linear model for good. So next time you turn on the tap or flush the toilet, just ask yourself, how quickly can we scale these circular resource factories so that every drop down the drain isn't just wasted, but actually powers our future? Thanks so much for joining me on this journey today, right here on The Explainer. See you next time.